Bratislava, who is going to speak about nature of massive neutrinos. So thank you very much for coming.
Oh, thank you very much for inviting me. I am pleased to be here at the University of Silesia, and I am also very pleased to meet here Peter Lichard, who was my teacher in Bratislava. And in my presentation, I would like to tell you something about neutrinos and about the importance of neutrinos. So here is the content of my talk. After some introduction, I will maintain the subject of the neutrinos double beta decay, both experimental and theoretical aspects, particle and nuclear physics aspects, and also the importance of supporting experiments to understand this process better. So what we know, neutrino is the most abundant particle in the universe. And there are many different sources of neutrinos. There's the cosmological, the relic neutrinos, we assume there are, but nobody has seen them. We don't have technology to observe them currently. There are neutrinos coming from the sun due to nuclear reactions there. There are neutrinos which came in, for example, from supernovas in 1987. We registered them for the first time. And there are also neutrinos which are produced due to nuclear reactions in reactors. There are some backgrounds on supernova. There are neutrinos which are produced in our atmosphere when the high energy protons are stopped in the atmosphere, and secondary particles are producing neutrinos. And there are ultra high energy neutrinos of origin we do not understand. They are related with some ultra high energy processes in the universe, maybe some collisions of black holes, neutron stars, and so on. We try to detect them, and we have seen them already with the neutrino telescopes. So we have only technology to observe all these type of neutrinos, and you see there is very big difference in energies that are produced. So nuclear, they are typically MEV, atmospheric JV, and here even these energies are about 10 to 6 higher as the energies are accelerated protons at LHC. But it is the only particle we don't know, elementary particle, we don't know the fundamental properties of this particle. So, but still about this importance, you see the time is changing. At that time, nothing was known about neutrinos. And now we know that neutrinos can answer very fundamental questions related with the origin of the universe and just the processes inside and all development. It is just relic neutrinos can tell us really something about the what was at the beginning of the universe. The neutrinos can also explain, due to effect of CP violation in neutron sector, the difference in matter and antimatter in the universe. We know that in the universe there are matter. When the astronauts came to the Mars, they did not annihilate. So we know that it's also from the matter. And the neutrons can be responsible also for dark matter and dark energy of the universe. There are some, we understand what is happening in stars, in sun, or by the supernova explosion due to neutrinos. And we assume there are some cosmic accelerators which can accelerate these particles to these high energies, which we already observed. And neutrons can tell us what is happening inside our Earth. We know that about the energy of about 50 terawatts is produced in the Earth due to nuclear reactions there, and we can measure it, this amount, with neutrinos. But normally we can only go into the Earth only a few kilometers, but with neutrinos we can understand what is happening in the Earth. Geoneutrinos were already detected by 2 experiments Kamland, and also Borexino. And neutrinos are telling us there is new physics beyond the standard model. Standard is very successful, as we know. And we can even, the neutrinos can have practical application, can help us to cross-check what is, due to security, what is happening in nuclear reactors. There are already such type of experiments. But after 93 years, neutrinos were proposed by Pauli, and 67 years they were observed by Reines and Kovan. We don't know much about them. We only know, due to observation of neutrino oscillation, we know there are three families of neutrinos, that they are massive due to neutrino oscillations. We know the relation between the flavor and massive states, mass states with just unitary matrix PMNS. But we don't know, are neutrinos Dirac or Majorana particles? What does it mean? All other elementary particles are Dirac, but by neutrino, because it's neutral particle, there is a possibility that neutron is own antiparticle. In that case, we call them Majorana neutrinos. If neutrinos and antineutrinos are different, in that case, we are speaking about Dirac neutrinos. We don't know much about CP violation in the neutrino sector, whether neutrinos are stable, about the magnetic moment of neutrinos, whether there is some additional flavors of neutrinos, so-called sterile neutrinos, or how many neutrinos there are, about statistical properties of neutrinos, are they really fermionic, or there is some bosonic component. There are some discussion about it. The most important issue is, however, the nature of neutrinos, Dirac or Majorana. And there is a lot of effort to establish the mass hierarchy of neutrinos. We don't know them. We don't know masses of neutrinos. We know only they are massive particles. And all these three aspects are addressed in the process which is called neutrinos double beta decay. But coming a little bit back, so we know that we have a very successful standard model. There is a lot of phenomenology beyond it. But in the standard model, there are only left-handed neutrinos, and so neutrinos are massive particles. Because to have massive, we need also right-handed component. But the most economical is the situation we have only left-handed components. So there are not right-handed neutrinos, and therefore neutrinos masses are zero. But all of these experiments with reactor, atmospheric, long baseline, accelerator experiments, they establish effect of neutrino oscillation, which proved that neutrinos are massive particles because this neutrino oscillation depends on mass square differences. Not on masses, but mass square differences. And standard model is the most economical. So really, but we assume it is only low energy approximation of more fundamental theories. So in theories beyond the standard model, we assume there can be energy scale, which is described by higher, more complex theories. And in these theories, we can produce so-called 5-dimensional operators. All operators in the standard are 4-dimensional. And this 5-dimensional operator can be of this structure. It is lepton duplet, Higgs, lepton duplet Higgs. There is some scale factor. And after some spontaneous symmetry breaking, we produce the vacuum expectation value. And we can create mass 10 only with left-handed neutrinos. It's possible because charge conjugation of left-handed gives our right-handed field. But this mass term is violating the lepton number. So when we make this global gauge transformation, we get this additional phase, and because of that, this term violates the lepton number. So if there is Majorana mass term, if neutron are Majorana mass particle, they should be processes with total lepton number violation, not flavor, total lepton number violation. We can, from this, estimate the scale. So when we assume we know that the mass is current constant from measurement from tritium beta decay and other, that neutron is below 0.3 electron volts are masses. If there are only 3 neutrons, the highest from them. In that case, so we have this quantity, we know the vacuum expectation value, some Yukawa coupling, and we can come to a quantity which is 10 to 16 JeV. So neutron masses can be related with the scale of 10 to 16 JeV. But there are many different models. The realization of this neutron mass generation in the great unified theory models with maybe right-handed neutrino, that is very right-handed neutrinos, we can again so-called seesaw structure that we have always mass matrix instead of 3 light neutrinos. So there is the standard model mass is 0, but they can be Majorana mass term associated with heavy sector. So this matrix is 6 by 6, and when we diagonalize it, we get 3 light and 3 heavy neutrinos. In one flavor, it is just, in one flavor, we get Dirac masses is mass of the approximately other quark and leptons. Here is the lepton number related scale, and here is additional dynamic mass. So we can strong separation due to factor for light neutron masses, and we have also high neutrino mass, a large neutron mass associated with the heavy sector. So this is the seesaw mechanism. There can be other type of seesaw mechanism like with Higgs triplet and so on. But we don't know what is the mass scale. It can be KV scale, it can be Fermi scale, TeV. At LHC, people are looking for heavy neutrinos. It can be also great unified theory or the Planck scale. There is no, there is no preference for any of them. Coming back, this possibility that neutrino can be Majorana particle was first introduced in paper of Ettore Majorana, who afterwards disappeared. But he published it only because he wanted to get a position in Napoli, and there are books about what happened and so on, with very nice stories. Possibilities that neutron as Majorana particle were also discussed by Bruno Pontecorvo, who was looking for who introduced neutron oscillations, and when Ray Davies was looking for neutrino oscillation from reactant with his reaction, from the neutrino is absorbed by chlor and argon is produced. So this reaction is only possible if neutron is coming and not antineutrino. And from a reactor come mostly antineutrino. So there were some rumors that Ray Davies see a signal from such a reaction. So these rumors came to Dublin, and it was Bruno, and he made interpretation. He suggested it is due to neutron oscillation, but oscillation so-called in the sterile neutrinos, and it should be a truly Majorana particle. Nothing was known about neutron flavors at that time. Here's the position of Steve Weinberg, who is saying that he believed that the neutron's mass generation is due to this 5-dimensional operator. So it's different from mass generation of neutron as from other elementary particles, other quark and leptons charge, yes? So this is the possibility. So to prove that neutrino, to solve the problem of nature of neutrinos, we need to solve this problem experimentally. And it is practically possible only with, by looking for a signal of neutrons gamma beta decay. So neutrons gamma beta decay is here. It is Furi and Rakach. Rakach described for the real neutrinos propagation. When it is nucleus virtual, it was with Furi proposed. So we have nuclear reaction. Nucleus changes the charge by 2 units. 2 electrons are emitted, and we see that 2 leptons are created. So the lepton number is not constant at the beginning and the end. And signal is that people are looking for a sum of energy of these 2 electrons. So there should be a peak in this spectra for the sum energy at the end, given by the Q value. But There is also allowed process, it's also second order process in weak interaction. It was proposed by Maria Guppert-Meyer, and in this case we have this continuous spectrum because they share the energy with emitted antineutrinos. And so the people are looking for the signal at the end of spectra. And it's possible to look for such a transition due to pairing interaction. Even nuclei are more stable as odd nuclei. So we can have a situation that energetic transition to neighbor nucleus is forbidden energetically, and the only open channel is by changing the charge by 2 units. So using the formalism on the field theory, one can derive the half-life for neutronal beta decay, which will equate this parameter, so-called effective mass of major neutrinos, and there will be some nuclear matrix element due to nuclear transition, some kinematic factor due to phase space, and so on. So this effective major mass, when we have mixing of 3 neutrinos of the PMNS matrix, which is parameterized by 3 mixing angle and 1 CP phases. But in the case of Majorana neutrons, we have 2 additional Majorana phases. This Dirac phase, we call it, these Majorana phases, are not entering in this parameter. So from all of this, this quantity depends on the 3 masses of neutrinos, 2 mixing angles, and 2 Majorana phases. We don't know the Majorana phases. We already know the mixing angles, and we know 2 mass square differences. And because from the oscillation of solar neutrinos, we have 2 small mass square difference and large mass square difference due to oscillation of atmospheric neutrinos. It's measured established. So now is the question where to put this mass square difference from solar neutrinos, up or down. So we then are speaking about normal and inverted hierarchy spectrum. And so this quantity which come inside, we don't know it, but we can calculate it with help of the parameters we know from neutrino oscillation. So as I mentioned what is. So that means we can take one parameter of these masses as free parameters. Majorana phases we don't know, we can take arbitrary as from 0 to 2p, and then dependence of this parameter on the masses of lattice neutrino can be shown like it is here. What is inside is due to arbitrariness of CP phases. This is for the different type of spectra. And so to establish the mass spectrum, we need additional information from the experiment. It can be taken if we would measure this quantity from the cosmology, which are measuring the sum of these 3 masses. We can take it if we would see neutronal beta decay, or from the measurement of single beta decay. We could have additional information which could tell us about the spectrum. But this quantity which is here, also here is the assumption neutrinos is Majorana neutrinos, we can have these 2 dependence for inverted spectrum and normal spectrum. So that are the allow regions. And this region is also disfavored by this constraint from the cosmology. And so the people are looking for a signal of neutronal beta decay in the case of different nuclear transitions. They are given here. The most favorable are those with the largest Q value and the largest natural abundance. So these nuclei were already considered in the real experiment, but with different technique values. So it was TPC chambers, just bolometers, scintillating crystals, and so on, liquid xenon experiment, or the trecocalorimeters. Where is this? I cannot see. Supernova trecocalorimeter. So therefore, it's expensive. So the prices of these elements, you have to enrich these isotopes. And there are different types of enrichment from germanium, molybdenum, telluride, some technologies. So already you need in other semiconductor industry or just by medicine. So you have the possibility to, or facilities which can enrich them. Yes, and a very important parameter to see for a signal of this peak is the resolution of the detector. And you see that the germanium detectors and the bolometers have very good resolution. But till now, they cannot distinguish the signal of gamma, which is produced due to gammas or electrons. So everything has some advantage, disadvantage. The technologies are improving. And here is the current situation with different type of experiments. So all should be in the underground to have practically zero background. No background from the cosmic muons, no backgrounds from the neutrons. You have some shielding and so on. And the half-life, these are the constraints. This is the lava constraints of the half-life of this process for these isotopes. You see that the leading experiment is Gerda and EXO, or Kamlanzen. And then one can get constraints of this quantity which is measured. And then we are already close to the region so-called inverted hierarchy. So people assume that if there is inverted hierarchy of neutron masses, this new generation of experiment will see it. And also zero background, as I said, is different calculated if there is still some background events or not background events in the peak. It is just the technical things on the experiment. The Kamlanzen is the first one-ton class experiment. They combined the results of Kamlanzen with 400 kilometers of xenon and 800 kilometers of xenon. The previous experiment was up to level of 100 or even less, 40 kilograms of enriched isotope. So they got the most constrained current limits. There is, this was on xenon, on germanium. There are a lot of activity. There were two experiments of Gerda and Majorana, and they are now combining in the Legend 200 with 200 enriched isotope 76 germanium. And they can come exclude already the inverted mass hierarchy when it will be finished. So this is maybe in the time scale of maybe 5 years, what is expected currently. Another type of experiment is with bolometers, so-called Cupid, Coor, and so on. So it is by low temperature experiments, and they are improving and assumed to come also even to the range of the normal hierarchy of neutron masses. So here are these most perspective experiments, Legend, Cupid, and EXO. And they will probably come to this region. And so this third is the NEXO. They exude even few ton of enriched xenon 136 with half-life 10 to 28. After 6.5 years taking data, they will come even to 15 MeV. So new EXO will come, which touch this region of the normal hierarchy of neutron masses. Of course, there are many theories beyond the standard model. Practically all of them require massive Majorana neutrinos. And there can be other mechanisms proposed, not only with this neutron mass. Due to neutron mass, there can be other mechanisms. So not only due to, for example, neutron mass is generated by 5-dimensional operators. So in that case, is the current limit. It can happen that the process is observed by even in this region or in this region for the parameter scale. There is so-called Schechter-Wallet theorem, which is telling us that if there is any mechanism of neutron alpha beta decay, you can connect these lines because you produce two d quarks and two u quarks. When you connect it with this double loop, it is a radiative correction to neutron mass. So any mechanism, if there is any mechanism of neutron alpha beta decay, it would mean that neutron is massive Majorana particle. So what are the possibilities? We can only 5-dimensional, you can have 6-dimensional, other dimensional operators, like it is indicated here. This is the standard proposed by Weinberg. We can have 7-dimensional operator, electron current, so with quark and so on, and other type of neutrino mechanism. And we don't know which of them might be the dominant. We suggested a so-called quark condensate seesaw mechanism for neutrino mass. So take into account 7-dimensional operators. 3 half 1 is give us 7. 3 half, and 1 it gives us 7. In that case, after spontaneous chiral symmetry breaking, the condensate, quark condensate produced, and we know there is quark condensate. So in that case, masses can be given by this parameter lambda squared. And knowing these quantities, we can estimate what should be the masses, because we know already the quark condensate, and we come that this lambda should be at the level of few TeV. So if this is the mechanism of generation of neutron mass, there is possible to see effect of Majorana neutrinos at the TeV scale. That means at the Large Hadron Collider. And if there is 5-dimensional operator, we can have two mechanisms, which we produce mass and just without producing mass. And we found that this is the dominant mechanism, and in that case, this contribution should be very small to neutron alpha beta decay. Knowing a relative strength of these two mechanisms, we were even able to exclude the inverted hierarchy of neutron masses and make prediction for neutron masses, and should be seen in single beta decay and in cosmology. So I remind you that current constraint from Katten experiment is about 300 milli-electron volts, so it should be much better. We don't have technology to see it in single beta decay currently, and from cosmology we expect in this range, which is not contradicting the current situation. Another possible scenario is that we have 3 light neutrinos and 1 heavy neutrino, which mass is unknown. In that case, the half-life is more complex, so we assume that the mixing of the heavy neutrino with electron neutrino, and is the dominant contribution. In that case, the matrix element depend also on the neutron mass, because in the denominators of the neutron propagator, the mass is important. There are two limited cases, so-called light neutron exchange, heavy neutrino exchange, and relative is different lepton number violating parameter. This is for the light neutrons, this is for heavy neutrinos. And we found that the half-life can be well described by so-called interpolating formula, which somehow simulate the behavior of the neutron propagator. So here is dominant the mass in the numerator, and here in the denominator. And it can be simply described. With this parameter can be fixed by the calculated nuclear matrix element for light and heavy neutron, with these two extreme cases, light and heavy neutrino exchange. People are looking for such mixing of sterile neutrinos. So we have one additional neutrino, we have only left-handed interaction, and the constraint of the mixing of the sterile heavy neutrino with electron neutrino on the mass, which can be different. Neutron beta decay can exclude everything up, even much better as this is from the Katten experiment, this is from the laboratory experiment of the accelerators, and so there are the current constraints on the mixing. So people are looking for it. Another possibility is very popular so-called left-right symmetric model, that we have, in addition to the left-handed neutrinos, we have right-handed neutrinos. Right-handed neutrinos have two sectors, light and heavy, left and right. And in that case, we have mixing matrix which for 6 by 6 for neutrinos, 3 light, 3 heavy. And by block can be, there are 3 by 3 sub-matrices. And we found that the relative mixing, using interpolating formula, the relative effective parameter in this case is for the light sector and for the heavy. And this additional lambda is parameter associated with the ratio of the light and left and right-handed vector boson squared. So the problem is, if the process will be observed, can we tell something about the contribution of light and heavy neutrinos? This matrix, unlike the previous one, we had only 3 mixing angles, 1 Dirac phase and 2 Majorana phases, can be parameterized with 15 angles and 15 phases. We found that for this internet formula, using different calculations of nuclear matrix, and that practically it doesn't depend on ice. That this is general for. Therefore, it will be not possible to establish by measuring on different nuclei whether contribution is from light on the heavy neutrino sector. And we even make a simplification due to seesaw. Let's have this interference parameter by 1, so-called seesaw parameter, and we have by block for light neutron mixing and heavy neutron mixing. If we assume such simplification, we can tell that using the unitarity of this matrix, we can tell that this matrix should be a Hermitian conjugate of the PMNS matrix. So we can now tell something about for the heavy neutrino sector, what was not before. But we still need some assumptions, so-called seesaw relation between masses, inverse or proportional. And when we do it, we see we can even understand the contribution from heavy neutron as the function of the lightest neutrino mass. And we see that this contribution can be dominant, comparable with what is currently measured. What I showed the previous figure. So there are for different scenarios. Here is just masses are inverse proportional, or here is proportional, and then we see that really we can have contribution from significant contribution from heavy neutrino sector, which can be dominant. But dangerous situation is we see this region. There is so-called strong cancellation in the case of normal hierarchy. So if it's below 10 to minus 3, even not future experiment or what can be discussed now will be able to make conclusion about it. So because of that, we are discussing also possibility of oscillation of real neutrinos to antineutrinos. And in that case, instead of this parameter m beta beta, we have parameter with distance due to oscillation of neutrino on this exponential phase. And for making this different ratio of distance and energy of this oscillation, we see that if even it's suppressed, we can have significant contribution. So one can discuss whether the astrophysical dimensions such process is possible, or with what kind of sources what we are now considering. People are looking for Majorana neutron at LHC with this so-called Kungsianovi process. So after collision of PP, right-handed vector boson is produced with decay on the electron and heavy neutrino, and with decay electron to jets. And people are looking for this signal at LHC, and they were only possible to exclude all this region, which is given here. And this is just what is excluded by neutrinos double beta decay, everything above. So there is some region of parameters this process can do better in respect of the heavy neutrinos, but it remains mostly that the potential of neutrinos double beta decay is much broader. All these experiments, in addition, they are looking for neutron double beta decay. They see also signal of 2 neutron double beta decay. It is the rarest process so far observed in the nature, with half-life about 10 to 18, 19, 20 years. And but we know the spectrum in the case of the 2 neutron double beta decay, but there can be some deviation. People are looking also for new physics on the background of this process. And it can be maybe due to so-called when a different particle like Myron is emitted. So we have 3 particles, so they share the energy with Myron, and Myron we cannot detect, but electron again, but it is a result of it with 2 Myron, 3 Myron, and so on. The position of the peak, so the maximum is changing. People are discussing this process also in respect of the so-called bosonic admixture of neutrinos, the Lorentz invariance factor, and so on. But this is the shape factor. In addition to the standard, they are looking for some small deviation due to the additional processes. They are also a result of our study. So by assuming, in addition to the left-handed interactions, that we have some right-handed interactions. They can be left-right-handed. In one we have 2 and also right-handed. Also, with respect to the lepton and hadron currents. And of course, if we have right-handed neutron, they can, with massive MeV range. So the spectrum depends. The Q is maximum is shifted in that case, and it is like interpreted here. Unfortunately, this figure is not seen much, but again, 2 neutron double beta decay can be used to constrain these parameters, which are also constrained from other processes, single beta decay, accelerator experiments. But these are the perspective of future experiments which can put constraints of the admixture, also right-handed currents, so-called exotic interactions or not standard interactions. This process is, for this process, very good super NEMO experiment. It's a trecocalorimeter. There is some foil inside. Where is the source? The double beta decay nucleus. Then 2 electrons are produced. They're distributing in the magnetic field, and just the energy is measured by the calorimeter and by the scintillators in this case. And so what is advantageous, one can identify the really electrons in this process observed. What is not possible in many of the other experiments. So if it is technology, once the process will be observed, this process can help us to tell or to identify also the mechanism, or to identify really confirm. But this technology, you need very big detector, trecocalorimeter, unlike in other experiment where the source is just a detector, what is in the case of germanium experiment. Just so one can study with this some nuclear structure effect and so on. I will not go too much details, but also very important point is, and experimentalists are unhappy of it, that we cannot reliably till now calculate nuclear matrix element for this process. It's a nuclear transition, so we have to calculate. We have many Boni theories, yes. Sometimes ago, there were uncertainty of factor 10 by, it was as Maruyama, Bachko, and other published this, and everybody was of set of it, but it initialized that practically all possible nuclear structure approaches, shell model, QRPA, project Hartree Bogolov, IBM model, energy density functional, are currently used for calculation of these matrix elements. We cannot relate this matrix element to any other process. That's the problem. These matrix elements have to be calculated. Additional problem is just effective axial coupling constant. Should be different from the free nucleon or not. Some analysis show that it can be strongly suppressed, and this is discussed now. So there are all these models that are used in the calculations, and to get it, we need we have to derive the nuclear transition operators, which include also higher nuclear currents and everything. The issue is the spin and isospin symmetries, because initial and final nuclei belong to different multiplets of the isospin and spin-isospin symmetry. So if isospin is conserved, that means that in that case the double Fermi matrix element is 0, but double gamma teller, due to small violation of SU4, spin-isospin symmetry is not 0, and therefore we see this process experimentally. So it's relatively experimental. It's the current situation with nuclear matrix element calculated with different approaches. The spread for different nuclei, you see factor 3. For light neutrinos, for heavy neutron situation, it was much worse. We made the calculation with QRPA and different variants. So due to a large model base, maybe we are doing better, as for heavy neutrino, for light neutrino is questionable. Additional problem appeared that recently people into so-called contact operator to ensure the renormalizability of the amplitude, changing 2 neutron to proton, emitting 2 electrons. And again, we have the standard approach with Fermi double gamma and tensor contribution, just the neutron exchange potential. Here are the structure of this Fermi gamma and tensor contribution was the main contribution here. And this contact term has a different structure. Included here, and it was evaluated nuclear shell and QRPN, and in percentage saying that it can be comparable with the standard approach, this contact term. It is also now discussed what can change the value of nuclear matrix elements. Another problem is just the problem of the big axial coupling constant, GA. We need additional information from relative experiments to understand what is happening. It can be experiment like, of course, from 2 neutron, single beta decay, muon exchange, so double pion charge exchange, the charge changing nuclear reaction. Also, there is some 2 gamma emission processes can offer similar nuclear matrix elements. Or just now with a lot of initiative in Catania in respect to heavy ion double charge exchange reactions. So you see the matrix of neutrons double beta decay, it is integrated heat, has contribution from different multipolarities of the intermediate nucleus. It can be, due to large neutron momenta, you can populate all multipolarity of the intermediate nucleus. And the 2 is for the light and heavy neutron matrix element, the distribution. We see that is 2 minus, a big contribution, and so on. But one can are trying to understand and relate also with related processes like muon capture. With muon capture, you can populate all the states of the intermediate nucleus because you have large energy available. To understand 2 neutron is also important. We don't know whether the contribution for low line state or high line state from the region of gamma resonance are important, because this matrix element, you have the double gamma teller operator, and you have the completeness of 1+ states of the intermediate nucleus, and it might be the transitions through these states are important, or through these states. Already, as it was measured already, this process, so one can see distribution of nuclear matrix element which are given here. It seems there is no proportion with calculated neutrons double beta decay matrix element. People are trying to, but I would like to understand this, because for 1 plus intermediate states, one can check the wave function we are using also for calculation of neutrinos, beta decay matrix elements. There are some pseudo, as it is a second order process here, there can be some sensitivity to the energies of the leptons in the intermediate states, and there are some analysis saying the so-called showing due to shape of the spectra. What we suggested that it can be, it indicates that the transitions to low-lying states are dominant, not pseudo gamma resonance. Here we see this process, half-life is given here. We can have the making Taylor expansion over the lepton energies and denominator. Denominators that are there because it's a second order process. All the second order processes have denominators, and in this appears lepton energy. If the transition to higher energy, so importance of lepton energies are less. And these analyses were performed with Kamlan-Zen experiment, which already were measuring so-called this parameter C is related with effective GA. C is the ratio of the two matrix elements which are in the expression here. One with the first order, and second with the third order power of the energy denominator due to Taylor expansion. There are some recently also published paper in Nature. The ab initio model calculation showed that if one takes into account meson exchange current and three-body forces, maybe one don't need quenching. So the formats are well established, and in that case they found that there is no need for quenching of the axial vector coupling constant. And one can consider just 1.0, 1.27, as 1.27 is for the free nucleon. This subject can be also discussed with the strength distributions to the intermediate nucleus can be discovered as muon capture, as we can populate to higher energies. Some measurements are done. Here is just the spectrum of the contributions from different energies of intermediate states. Also, it is you have processes with 1 nucleon, 2 nucleon emission, and so on, but they can measure it and indicate there is also a lot of strength. Therefore, it's confusing. The neutronal beta decay is just governed by transitions, it seems, through the low-lying state. So still is question whether we need, and this can be related with higher multipolarities, and therefore everything should be cross-checked. So we made also analysis for muon capture rates, because muon captures were measured for many isotopes, and we found that we need practically no quenching, theoretical, this is just one should be, assuming quenching GA 1.0, 1.27. Other experiment calculation were showing 0.4. It should be low. It would not agree well with the experiment. So here is the width of this process of muon capture. Here are the experiments and our calculation with different GA. We see that practically no quenching is needed, and here we calculate also contribution of different incorporate for A76, A36, distribution of the contribution from intermediate nucleus from different multipolarities. This is the matrix element, neutronal beta decay decomposed, and here comes from the muon capture. In Catania, there is new initiative to understand this matrix element. People are measuring so-called heavy ion double charge exchange reaction. In such process, in heavy ions, one can come, for example, for selenium to germanium, for germanium with selenium, with probe, like here, neon goes to fluor, or neon goes to oxygen. So at the beginning we have a beam of neon or just opposite oxygen, and one can consider these transitions here. And one would like to measure transition to the ground state, and it seems it's possible. So this strength to the ground state is only a small fraction of the full strength to the nucleus A Z plus 2. So one can also check this transition, but the interest is just to the ground state. And it seems they can do it because they already understand all possible transitions. What they already measured here, they see for the ground state some cross sections. So from this cross section, the nuclear wave function can be tested and used for calculation of neutron and beta decay. So it is just on the beginning this project, both experimentally and theoretically. So there's still some time to complete the job because we are waiting on observation of neutrons and beta decay. We have only a level limit for the half-life. So we are at the beginning of the road, so different approaches, and everything of this can help us to get some reliable nuclear matrix for this process. And all these particle and nuclear physics aspect of neutron and beta decay were discussed in different review articles, which are presented here. So there is a long interest to this problem. And my final slide is that it happens so that the mankind, somebody addressed some interesting problem to the mankind. Long time ago, it was Pierre Fermat who told that there is no solution of this equation for other than n equal 2. And it was, after 358 years, it was solved by Andrew Wiles. Yes. Here it was beginning was Ettore Majorana, who told us neutrons can be own antiparticles because they are fully zero. After 85 years, we are coming to the Thom experiments, Thom scale experiments, and so we can probably come to the level of the effective mass of few milli-electron volts. But what in the case the effective mass is smaller, cannot be excluded. We don't have technology for it, so maybe we will need to wait a little bit more. Thank you for your attention.